So like let me recap that because the meeting just started. So machine learning is a part of AI that's to do with giving computers the ability to learn, right, from data without being explicitly programmed. So previously, traditional programming, what we do is like we do like pattern recognitions, or we do like if statements, things like if Daniel is in this place, then it means Daniel is here. If Daniel is not here, it means Daniel is not here. Now those things are just explicitly programmed, given some if statements. If the number is from 0 to 1, then say that this guy is probably a guy or a girl, right? Now those are if statements, and that's how we've been running until machine learning became a big thing, until it surfaced the internet. So machine learning now came in, and you could just give it data, you could just give it information, and it learns from the data, identify patterns, and then decide, make decisions, right? Make decisions and like tells you like this is what I think is the correct thing, this is what I think is the prediction, this is the right thing, yeah, right? You don't need to write some code, you don't need to like write some hard code for it to be able to give you very, very good answers. Now, 1 minute. Let me make sure I'm using the right microphone. Okay. Hope you can see my screen. All right. Can you see my screen? Can you see my screen?
Yes, you can see us.
All right. So under machine learning is a branch under AI, right? It's a branch under AI, and then under machine learning we have deep learning. Under deep learning we have computer vision, we have natural language processing. Before we now have LLMs like ChatGPT. Under machine learning, we have reinforcement learning. We have I think I already showed you guys this thing last week. So let me recap because we need to take it from head to toe, introduction to computer vision. So if you look at this, you see that AI has a lot of branch, right? Under AI, we have machine learning, we have vision, we have robotics, we have speech, we have natural language, right? Now, in this machine learning, most of these things like this vision falls under machine learning. Although we can do computer vision without machine learning explicitly, we can run some pattern recognition without even needing to train the machine learning, the software. We can run some pattern recognition. We can run some traditional computer vision models out there, right? But it is in the age of machine learning and deep neural networks that we now had to go deep into computer vision. Because with deep neural networks, everything started becoming easy, everything started becoming um, more accurate. All right. So, um, under machine learning, we have deep learning. Under deep learning, we have things like natural language processing coming up. Um, 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 and then from there we have large language models and also computer vision. But it is said that all these guys came up from data science, which is more like trying to understand data. All right. um, so now, what is machine learning really? So in machine learning we have three types of machine learning, but I decided to put out these two. We have unsupervised learning, we have semi-supervised learning, we have reinforcement learning, and we have supervised learning. So I'm going to start from the two that is not here, or reinforcement learning. Reinforcement learning has to do with the part of AI that teaches that AI learns things by itself. Now, how does it learn things by itself? It literally learns things by making mistakes. When it makes mistakes, it reward himself. So um, let me show you guys reinforcement learning. I'm gonna give you guys example of a robot that was trained under this. Most robotics as a whole, most times they use reinforcement learning to make robots to learn, to make robots to learn, and with that they can get better at things. One sec, need to show you guys. Need to make sure you guys understand this thing, because if you don't understand it, it's gonna be so hard for. If you don't understand, it's gonna be so hard for you guys to catch up everything. Get into AI for solving. Yes, I think it is down here. Okay, I think I can just show you guys this too. So, um, so we have supervised learning, unsupervised learning, right? So unsupervised learning, basically, I'll explain that later. So reinforcement learning is an area of machine learning concerned with how intelligent agents ought to take action in environment. So they like reward themselves. I'm looking for a particular video. Ah, it has gone. Okay, I'm coming. Robot training. It's a very, very old video that explains. I think it's Atlas, right? Atlas. Okay, so let's use this for example. So this robot you are seeing here is using reinforcement learning to learn. So what happens is we give it a set of tasks, we tell it to accomplish a particular set of tasks, and we leave it by itself. Now, if it does the task wrongly, it rewards himself with what? With a point zero. If it does the task rightly, it rewards himself with a point one. Meaning, for example, if the robot is working and you hit it and the robot falls down, it literally rewards himself with point zero. And next time, when you try to hit it, it's going to try to balance himself because it knows that that's a negative reward that it's getting. This is how most games, you see games, most games, some games, they use reinforcement learning to get like some hard levels. So you discover that you play a game and the more you play, the more the game gets harder. These are some of the things they use. But in robotics, they use it every time, as you can see. This robot is gonna like go through some rigorous process, and if it falls down, it rewards himself with zero. And if it's being pushed next time, it's not gonna try to fall down. Rather, it will try to stand still. So that's just a part of AI. Um, okay, for example, this one. So if they do the task wrongly, they reward themselves zero. If they do it rightly, they reward themselves with what? With one. Let me check. Let me check. Let me check if I can find a more better explanation. But wait, do you guys understand what I said? Do I like? Should I explain more? Can you hear me? Am I muted? Hello. Hello.
We can hear you.
Okay. So I'm looking for some very very good examples to use. A situation where like the robot did something bad and it was struggling. I can't find it. It's a very old video. Yeah. So that is reinforcement learning, right? It learns from mistakes, it learns from error. And then we have unsupervised learning in machine learning. Unsupervised learning has to do with like you giving it unstructured data or unlabeled data. So I just come to this room and I throw apple, mango, quiver. I just leave it there. And the AI model tries to recognize different patterns in all of them and group them together. Now this is called clustering algorithm. Uses clustering algorithm. There's a lot of them. There's neighbors and the rest of them, right? So it tries to find patterns in the data set you're given to it and then cluster them together. So for example, like this, no labels, it finds structures in the data, it pass it to the model, right? Finds structure and then can give you results out of um, just recognizing patterns. So clustering image patches, grouping similar texture, whatever thing. And then there's supervised learning. Now in supervised learning is the most applied, is the one we apply mostly. This has to do with giving a machine learning model labeled data. For example, like I give it image of a cat versus dog or image of an apple, and I give it an annotation saying like this is an apple and this is an object. This object is called apple, and that's a label data, right? Then I train the machine learning model. When I train it, I expect it to predict that if I give it a particular image like this apple, it should tell me it is an apple. Why? Because I have told it that this is an apple. So this thing is not magic. It's not like there's no magic happening in AI. It's just simple mathematics. It's just simple input and output. There's no magic happening. If you don't give an AI data, it won't understand anything. In AI, in machine learning, data set is AI's food, is machine learning's food. The amount of data set you give to an AI model is how good the AI model is going to be. No matter how much you tweak it, no matter what you do, a more good data set gives you a better machine learning model out there. So there's no magic happening. All right. So recap. Supervised learning has to do with what you give your machine learning model label data, and label data I mean like give it data and then you tell the machine learning what the name of this data is. All right. And then you train it, and then when you give it something next time, it can predict that yeah, this is an apple, this is a cat, this is a dog. Unsupervised learning has to do with like giving it some random bullshit, like you bring apple whereby it just mix it, you give it to it, and it should find patterns and tell you what it is. The example of this is a cat versus dog classifier, defect detection or whatever thing. The model learns a relationship between input image and output classes and then returns you an output. All right. I think this is really simple to understand. I'm trying to like break everything down. When I'm going to do the math part of it, I would like try to explain it in a very, very simple way so we all understand. So now, traditional machine learning algorithm before deep learning, we had they worked, right? But they couldn't do a lot. Like k-nearest neighbors, all right? Support vector machines, decision tree, random forest. You can go and like check about them, but these are the machine learning algorithm that we had before deep neural networks became a thing. All right. And these guys were working, yeah, but they couldn't do a lot. They couldn't do a lot. They could just do as much as they could, right? But I think till now people still use them. People still use them till now, although you rarely see like most of these applications come out with them. Or maybe I feel it's because of the hype from large language models. Everyone right now forgotten about like a lot of things, forgotten about some basic. People don't even care about learning AI from math. You know, they just feel like I'm an AI engineer because you can prompt ChatGPT, which is really wrong. Everything starts from math, right? All right. So the limit of these traditional machine learning models are they struggle with large data set, they struggle with like high complex data set, and they had to describe with simple features. For example, if recognizing first requires understanding title details. You see, um, what I meant to say is recognizing, for example, someone's face requires a lot of processes. First of all, you have to turn the image to an array. After turning the image to an array, you have to perform like some feature extraction. You have to do a lot of things, and this is really hard for these traditional ML models. And that's where deep learning comes in. Deep learning can handle all these things in a very, very flawless manner. All right. So what is deep learning now? Deep learning is a subset of machine learning. Now you're hearing me like mention deep learning, machine learning, AI. As I said, machine learning is under AI. In AI, we have a lot of things. In AI, we have computer vision, we have machine learning, we have fuzzy logics. We have machine learning is big. We have fuzzy logics, we have let me check it out. Branches of AI. So yeah, we have fuzzy logics, we have expert systems, we have natural language processing, we have neural networks, we have machine learning, we have robotics. Now, your car, some of your cars they use this algorithm, this physiology algorithm. The cars you drive, some of the cars you drive, some of these automatic manual cars, they use this system. But these things were not a big deal then until deep neural networks became a big deal, until like deep neural networks surfaced the internet. All right. Yeah. So deep learning is a subset of machine learning. It's under machine learning, basically, right? That uses artificial neural networks with multiple layers to enable computer to learn from and make prediction from data, similar to how human brains work. You know how human brains work? We work with like some neurons, nerves connected from this to that. Human uncle. So exactly the way human brain works is how a neural networks or an AI model works. So if you can see, we have this your this is cell body, right? We have all these little things. We have the human brain neuron. We have everything linked together. Let me find a very good example. Okay, let me see this. So I'm not good in biology though, but I'm using it to explain. So just the same way our brain cells is being linked together with neurons and different cells is exactly the way deep neural networks more work. Exactly the way machine learning works. All right, just exactly the same way. So in deep learning, we have neurons, we have layers, we have nodes. These things combine together to form a deep neural networks algorithm, and that's what makes it to learn and learn very well. So this method allows machine to recognize complex patterns such as image, speech, text without being explicitly programmed. Example, instead of telling the computer what feature to look at, the computer learn from those features automatically. Now I'm going to explain each of these. So um a neural network is like a stack of layer. So now this is where our our main learning will start now. Hey, it's already 10:32. Man, saying let's get started. So we have the inputs. These are nodes. So we call this thing nodes in deep learning, right? These are nodes. We have these guys, right? So let's say this is the first node now, and then this is like the second. This is like 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the output. This is our x, our input. So now everything you're seeing right here is called a node. This is called a node. Just like how our human brains works, right? These are layers. So in this simple deep learning model or deep learning algorithm, we have the first hidden layer. So we have the first layer one. We have layer two. These are all layers. Layer two. We have layer three. We have layer. We have the output layer. All right. So this right here is our input layer. This is our input layer. All right. This here is our hidden layer. This is the hidden layer one. All right. And then we have another hidden layer what? hidden layer 2. So this is an hidden layer, this is an hidden layer, and this is an output layer, which is going to be our y or our prediction. Now, how does this thing links together? Like, how does it link together? How do we pass information? How do you pass a human? How do you pass a picture of a human being from an input layer to an output layer? By next week Monday, I'm gonna write an a deep learning model from scratch with pure math. We are gonna link. We are gonna do an image prediction, picking a particular image with just numpy, no TensorFlow, no nothing. Pick an image, convert the image to an array, pass it through different neural networks layers, and then predict it. But how does this work? So what happens is we connect this input node to each of them. So each of them are all interconnected to each other, right? This guy is connected here, this one is connected here, this one is connected here, this one is connected here. The same thing, this guy is connected here. This node one node two is connected to hidden layer node two. This is connected to hidden layer node three, hidden layer node four. This node here connects here and connects here. This node connects here and connects here. This node connects here, and then this one connects here and connects here. So now what happens behind the scene is that as we keep on passing this information from this place to this place, the AI model keeps on learning. Now, for it to learn, there's a lot of things that happen inside here. We have activation functions, we have a lot of math going here. Last week I told you guys about y equals mx plus c, linear regression. It was very, very important, right? Y equals mx plus c. I remember telling you guys that we need mathematics to be good at AI. And I told you guys I'm not going to try to do a lot of maths. I'll try my best though, so I'll not disappoint. But you guys need to understand it, right? This is what helps us to pass information from one layer to the next layer, from one layer to the output layer. This is what happens basically. All right. So for an AI model to work so well, we use this simple equation for line slope of a line to connect it. Now this is what your vectors. So if you've done vector, you see different vector manipulation, dot vector, the rest of the thing, right? All right. Okay. So one use metrics and do a lot of things play around. So we use these. We each of these has weights, biases, right? And then activation functions. I'm going to explain each of them in this session. I don't want to like skip and explain everything at once. Um, where is my slide? All right. So a neural network is like a stack of layers that each learns something simple. Layer one learns edges, for example. Layer two learns shape. Layer three learns objects. Layer four learns the whole image. Each layer built on top of the previous one. That's how they get becoming. That's how they become smart. So from shallow to deep shallow network. So one or two hidden layers, deep network, three or more hidden layers, very deep. Any layers can learn from simple patterns. So what this means is right now I have just a very, very simple deep neural network. This is just one hidden layer, these two hidden layers, right? But and this hidden layers, one node, two node, three node, four node. It works, right? It works. It can do things for you. But out there, a model like ChatGPT, if we check the architecture, the or a model like YOLO, for example. So these they are models that have a lot of complicated thousands of layers, interconnected layers of neurons, a bunch of them, a lot of layers out there, right? So what we're just doing right now is just a simple shallow neural network, right? Just simple layer and then we're good. But the more layer you add, the more depth it gets, the more it understands things, the more it gets smart, the more it learns. And that's how we manage to get a lot of these deep neural networks with a lot of layers. All right. Um. All right. Okay. Let me get back to the slide. So I wrote some notes here. Why depth helps. So we have one or two hidden layers, right? Deep networks, three or more layers. So um models that we consider to be deep has like more than three layers, right? Now, why does this help? Because each of the layers literally does its own job. This one recognizes the age, this one recognizes colors, this one recognizes patterns, whatever thing. Middle layers can learn parts like eyes, nose, whatever thing. Later layers can learn the full concept like the face, cast, words. Now, this simple thing is what helps us to get very, very good deep neural networks model. Now, mind you, in the previous traditional machine learning practice, we didn't have all this in play, right? We had to like add code, do a lot of things by hand, and it was damn hard. All right. Okay. So now, what is activation functions? Activation functions is what allow neural networks to learn non-linear and complex patterns. So now, what are non-linear and complex patterns? I'm going to give a very, very good example. Let's say I'm building an AI model for classifying if an image is an image of a cat or image of a dog. All right. And then I have this. Um, Come on, I want to draw on this. So, mhm, you know, so what's going on here? I can't seem to see the pen brush. Delete. Interesting. Oh, yeah, look at it. So, let's say I'm building an AI model, a simple computer vision model. Most of the thing I'll be talking about is going to be linked to computer vision, right? This model is meant to take in image of a cat, right, and a dog. So this is our input x1, input x2. Now, I'm meant to take this model and then make it to predict for me if the image it is seeing is literally an image of what? Of a cat and of a dog. And after I did like a lot of my computation, I got some I got some figures out like 0.9 or 1 point something or whatever thing. We need to make sure that this returns only 0 and 1. So anything in between 0 and 1, if it returns from 0.5, then we are saying that this is an image of what? Of a dog. If it returns 0.6 up, we say it's an image of a cat. So now what do we do? Which deep learning activation function do we use to achieve this? Or what do we do to achieve this? Now what happens is that when we finish computing this first layer, right, we pass this from year to year. Before this passes year, we apply this to what is called Z. This Z is what is called an activation function. So so what happens is, let's say I have this guy to be x1, this is my node 1, node of hidden layer 1, this is node of hidden layer 2. Now we apply what is called a weight. So in this place, there's going to be something called a weight and a bias. Now, what are these two things? These two things are parameters that are used to tweak your model and make your model to learn. So they are those random numbers you set to make your AI model to learn, right? So let's say I want to get to this neuron, this particular neuron called N1. How do we connect this from year to year? We just do a simple thing. This guy has a weight, right? And then this whole layer has a bias. But each of these is gonna have a weight. Each of these, I'm gonna recap what I said. Each of these is gonna have a weight. But this whole layer has a bias. So how I can do this is by doing a simple math. I'm gonna say this is my neuron one, right? Neuron one is gonna be equals to what? It's gonna be equals to um x1 x1 times. So this is a simple formula. The formula z is equals to w times x right, plus b. Now this b is a bias that's been given. This w is also a bias, is a weight that's been given. We just set some random numbers. So what of a situation where we have a lot of nodes and layers? So that's where we do something like z is equals to what? Wi. This wi subnode I means of any number here. So if let's say for example I'm calculating for weight of one, or weight of, so I'm going to put one here, right? Times xi. So let's say this is xi. So that's going to be x of value I plus what? Plus b. Now these are simple things you must have learned in school, subnotation. I think there's a place here where I explained them. Um, okay, I didn't explain it. All right. So for me to pass this, I just pick this x1, I multiply by the weight, right? The weight, and then add it with the what? With the bias. This bias here, which is gonna be a random number, and that should give me what? It should give me, let's call it z. Now before we pass z to the next node, because after we've connected this to this z right here, this particular node, let's say this is node one. Before we pass this from here to the next node, we need to apply what is called an activation function. An activation function is what helps user model to be linear, for example. So we want this thing to tell us that this is an image of a cat and not of a dog. So we pass this guy to a function that helps us do that. And we have a lot of activation functions. We have sigmoid function, relu. What does each of them do? So let's say, for example, our input here is input 0 point something something something. We want to map it to either 1 or 0. We want to map it to either true or 0. And that's where an activation function comes into play. All right. So activation function learn nonlinear and complex patterns. So for example, sigmoid function output value between 0 and 1, often used for binary output. For example, what I say right is a binary classifier, which classifies if it's an image of a cat versus an image of a dog. All right. And then we have relu. I'm gonna go with this one, then I'll mention this. Relu um find the max of what? Of z, which is what? This is our z here. All right. Find the max of z. Very popular for hidden layers because it trends faster and helps with vanishing gradient. So relu literally takes from 0, right? It takes from 0 to 1. So it goes from 0, from 0 up. Um, yeah, from 0 up. And then a sigmoid function takes from 0 to just 1, meaning any value you get here must be in between 0 and 1. It is a must. And there's a formula for that. It must be in between 0 and 1. And this is mostly used for classification tasks, but this is mostly used for other tasks where like I want to like check for like probability of things or whatever. And then we also have the tar function, which outputs between -1 and 1, center data around 0. So the tar function is something that looks more like this. It looks like this. So this is it. just comes here, and then it goes like this. It goes from 1 to what? To -1. All right. Okay. So where do you apply them? Let's say you want to build, let's say you want to build something that should classify if this is an image of a a book or image of a bar. This is the best activation function to use. If you want to build something that classifies if this is an image of a cat with an image of a sorry, if this is the probability that this is actually if there's a probability that this is meant to be a boy or meant to be a girl, but you're not sure, like you just want to run probability, you can go ahead to use Relo. All right. Okay. So how does neural networks learn? Training neural networks usually follows these steps: forward propagation, pass input through the layer to compute prediction, and then it compute the loss, which is the cost function, measures how far the prediction is from the true target. Right? How far is the prediction from the actual thing that we want? And then it runs a back propagation, compute the gradient, and then does what? And feeds it back and train itself. So the gradient descent updates weight and the biases to the direction that reduces the loss. Repeat many times until the model performs well. So what am I saying here? Literally, we have this guy. It it does a forward propagation, pass input from this layer to this layer to this layer. Now, in the process of passing this thing, it goes through an activation function, and then when it gets to this output, let's say this is the output, the final output, it runs a cost function. Now, a cost function tells our machine learning model how far the prediction that we've done is from the actual thing. So, how far is this thing literally doing the right job? Is it how far is it predicting a cat from a dog? So, something more like this. So, let's say I have this graph here. So, let's say I have this graph here like this, and this is meant to be the real prediction. And then the AI model, this is linear regression though. This linear regression though. The AI model predicted that the correct thing is meant to be on this line, right? Now the distance between this place here and this thing, the actual thing here, is what is the cost. So we need to have a cost function that checks how far the main thing. This is the AI is meant to predict. The AI is literally meant to be predicting this thing right here. This one here is what the AI is meant to predict. But it went and predicted the wrong way. Like it went and landed on the wrong spot. So how far is this thing here, this data here? How far is this data from the this line? How far is this line actually from the real data? Right? And this is what we do with a cost function. So we use a cost function to determine how far this is from the real data. So, and with that, we can now update this weight and bias. We use that to do what? To know to update the weight and bias. But before that, we run some back propagation algorithm. True. Then the back propagation algorithms comes and updates each weight and bias, and then we do the thing over and over again until this is close, until this guy probably start predicting very, very close. For example, start predicting very, very close and comes close to this place. And then we say, yes, the AI model has learned. So that's what we are saying here. We compute the loss, measure how far predictions are from the true target. Then we use back propagation, compute gradient of the loss with respect to weight and bias. Gradient descent update the weight and the bias, the direction, and reduces the loss. Repeat this many times until the model performs very, very well. So parameters, hyperparameters. Oh yeah, this is what I'm looking for. So these are learned by the model from data, right? So we have weights, biases in the network, and then the upper parameters are being set by you and chosen by you at first. Then we have what's called learning rate. Learning rate is going to be used to determine like how far this thing is learning from each other, the speed at which they're using to learn. And then we have numbers of layers, numbers of neurons per layer. Then you can choose your activation functions, a number of training epochs. Um, Training epochs literally means the amount of times you want this thing to happen. This particular process of passing this input from year to year and then passing it back to year, passing it over and over again. That's why it's called the epochs. That's why it's called epochs. The amount of times you run the model from input to output, from input to output over and over again is called what? Epochs. I'm just gonna give today. I'm giving like a ground break to make you guys to just fit these things. And on Monday, I'm going to like go deep into these neural networks, and then we get to build one neural network from scratch. It's going to do an image prediction from scratch, no model, no nothing, everything from scratch, and then you understand it more. So, let's. What's the time? Okay, we have 6 minutes. So I'm gonna like solve this thing from ground and make you guys understand basically how it works. Let me check if I can join with my phone so I check my camera if you can use my iPhone camera. iPhone, am I even doing? 1 minute. I don't think this is possible though, but let's see. I don't think I can use my phone as a camera. Quick time. All right. Okay, I'm gonna try to use my phone as a camera. Tell me if you see my phone. Can you guys see the screen? Can you guys see? Can you see? Hello.
Yes. Yes, we can see.
All right. Okay. So I'm going to do like a very simple deep learning network here, and then try to compute it so you guys understand what's happening. So let's say we have this, right? We want to like compute a simple deep neural networks algorithm right now. How this thing turning like this? So the camera is using this. Okay. This is confusing me. One sec. Okay. So we have an input layer, right? So I told you guys these are hidden layers, right? So we have this. Let me use this for example. Just a simple um just a very simple deep learning algorithm. Very simple. We just um with just one layer, right? Only one layer here. With just one layer and three inputs. So let's say we have input x1, um input x2, input x3, and then we want to like produce an output, right? So we are meant this guy is meant to feed. Oh, sorry, you've not been seeing what I mean. So we have this layer, just this one layer, a simple layer that takes inputs one, two, three. Mind you, I told you to link a node to link a node, right? To connect between a node, use this formula y equals mx plus c. In this case, we're working with our z. So this is gonna be the output layer that we're looking at, which we are calling z here, all right? Which is gonna be what? Z is equals to, we have a weight here. So each of these, as I told you guys, has a weight, which are some random numbers we choose, and a bias. And this bias is for the entire neural network hidden layer. That's going to be W times what? W times X. So let's say this is X1 times X1 plus bias. Sorry, W times X1 plus bias. But I want to add all these guys too because I need to pass each of these guys to this particular node. And that's going to be W times X1 plus W, let me call this, yeah, W times X2 times X2 plus W times X3. Now after doing all this, we now add it with the what? With the bias. So let me recap with um, a two node layer. So let's say we have this and we have this, and then we have the output to be this. We have this, we have this. These guys connect here, and then we have two inputs, x1 and x2. Now we are looking to link x1 to x2 to, let's say, z1. This is not our first activation, right? This is z2. But I think we're looking to link this to this and then link this to this, all right? And then link this to this. And then this goes here. Then we have our output to be what? To be y. All right? This is gonna come here and then this is the z what? This is z1, z2 of hidden layer of layer what? Of layer one. It's gonna be of layer output layer two. This is gonna be what? Let's say z2. So how do I connect this guy from here? How do I connect this guy from here to here? How do I connect this guy from here to here? Simple. Each of these guys, each of these node has a weight. So let's say this is weight one, this is weight two, right? And this whole hidden layer has what you call a bias, right? So if I'm to link this guy from here to here, then link this guy from here to here, what am I going to do? To find this, I'll link it back to what? To here. Which is going to be what? My Z1 will be equals to this first weight times X1, right? Weight 1 times X1 plus this second weight, sorry, weight 1 times X2. Weight 1 times X2. Then now add it with what? I now add this 2 with my bias, with bias. And that's going to give me this first Z here. All right. And now with this, I can now pass this to what? To an activation function. We need to pass this Z to what? To an activation function, which is going to help us to do what? To set this value, to help us to know if this is actually closer to 1 or it is closer to 0. And one of the things we can do is to pass it through this activation function called sigmoid. This is actually one of the basics. Sigmoid function. Now what does sigmoid function does? Sigmoid function takes our input and make sure it maps it to just between 0 and 1. So this is 0, this is 1. Just make sure it maps it between just 0 and 1, and it doesn't allow it to pass here. So um so this is my 0, no, 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 0.5, yeah, and this is 1. Simple. So once I get this z, I pass it through this activation function. This is gonna be what? This is gonna be activation. This place now change to activation function 1, which is going to be what? Z, z1. So now after we've gotten this now turns to the value of this particular node, and then we pass it here and do the same thing again. How we get here is what? This z is going to be what? A1 is going to be A1. I know this A1, right? It's going to be A1 times the weight. This guy will have a weight. That'll be A1 times weight. Weight. Let's say this is going to be weight 2 plus A1 times this is going to be A2, right? So by then we must have computed this A2. A2 times weight 1. Let's say weight 1 here plus the bias. This will give us the second Z. This will give us Z2. To give us Z2 is equals to this. And then we now pass this to what? To another activation function. So we pass it to an activation function. Let's say, for example, sigma the activation function. Activation function. And that gives us the value of this here. And after this, we now find the cost function. So the cost function is what tells an AM, a deep neural a machine learning algorithm, how far our prediction is from the real thing, which is always most times y hat minus the real prediction value. Y hat, y is just a simple intonation, just minus the thing we predicted. This is the prediction. Y hat is the prediction. Let's say we predicted 2.1. The real value is what? Is 1. So we minus this by the predicted value by the real value, and that should give us like 1.1. And this is still far from the real value. Now we pick this, we run some gradient descent. Now this has to be the calculus back um divariant calculus which I'm going to try to teach you guys on Monday, right? So we use this, we find the dx dy and plot like some, we plot gradient descent basically, and then we use that to pass it back to the input. Now this is going to use this to act to tweak the weight and the biases. This we use it to tweak the weight and the biases, and then we do the same thing we did again. We repeat this process over and over again. So aside from gradient descent, there's a lot of other activation hyperparameters and a lot of things that we can do. So this is what happens behind ChatGPT. This is what happens behind your facial recognition. This is what happens behind every AI you're seeing out there. It is this simple math. And you guys have to understand this very, very well before you get into computer vision. So I'm gonna use a very, very simple example. Let's just do a simple maths, a simple layer, and then we move on. So I have an example here on my phone. I have an example here on my phone with hold on, let me write it down, then I'll share the screen again. So I have input 1, 2, 3, and then weight 0.1, weight 0. Weight -1, weight 0, and then weight 1. And this is my output. So I'm passing this with my x1. I'm gonna turn on my camera now. I'm trying to read out the note I've had here. X3. And then we are passing it here, here, here. These are output Y. Um and the next our bias is what? Our bias is have a bias of B equals 1. Okay. So let me go back. So this is what I wrote down, right? So let's say we have this simple one node neural network. My hand is paining me right now. Interesting how this thing behaves. Interesting. So let's say we have this simple one node neural network, right? Hey, wait, whoa. Someone stress me to that. Be waiting there happen. Okay. So our x1 is what? X1 x1 is equals to 1, x2 is equals to 2, x3 is equals to 3. And I told you guys each of these things has weight. So this particular guy has a weight of has a weight of, let's say, like weight 1, we apply weight 1, weight 0, weight this. So we pick this guy, the weight here, we multiply by this time this. 1 times 1 will be 1, and 0 times 2 will be 0, 3 times 1 here will be 3. We add all of them together, and that should give us, um, I think this is 0.1. Anyways, we add all of them together, and then we add them with the bias. So let's say the bias is b equals 1, b equals 1 plus b, and that should give us what? That should give us y. That's how simple it is. So I pick this, the weight, I say weight 1, add the weights with this, add this time this, plus this time this, plus this time this. All right, and with that we can get our y predicate value. So it's as simple as that. It's as simple as that. Very, very simple. I think it's still gonna be very, very a little bit confusing because most of you guys, I'm sure you have not played around with this thing before. But I'm gonna like end there and give you guys some assignment, which is gonna make you guys to go and do some in-depth research. And on Monday, I'll come back and explain this thing again, and we get to build it from scratch with Python, and we build an image classifier with it. So basically, we'll get an image, convert the image to an array, build a classifier, detect if it's actually an image of a cat versus dog, and you would understand how this thing works real time. And that is how you should get into computer vision. Without it, you will just be vibe coding and doing things, and you'll just be a terrible AI engineer. If you're employed to do a job you can't deliver. I would like you guys to ask questions, please. I didn't cover all the activation functions. I didn't cover them well. Sigmoid function. I meant to show you the formula. The formula for sigmoid function is 1 over 1 exponent. Let me check. Formula for sigmoid. I'm going to cover all of those next week. Today is just an introduction. Hope you can still see my screen, right? Can you guys see my screen?
Yes, you can see a screen.
All right. So, so after you've done everything, this is what you're going to do. You pass that value you got from x to this particular formula. It's a very, very simple formula. 1 over 1 plus exponent of minus x. Simple. You when you run this, no matter what you do on planet Earth, even if your output x is 1 million, it will equate it to 1, no matter what you do. No matter what your y gives to you, no matter what your output here, this particular output, no matter what it gives to you here, once you run this, it will equate it to 1 or below 0.5. So next week I'm going to like explain everything well for you guys. Today is just an introduction to deep neural networks, and next week I'll break it more down and we'll get to build something with it. And then we get deep into computer vision, padding, strides. I'll explain yellow architecture, explain a lot of things for you guys. At the end of this, at the end of this session, this boot camp, you should be able to build a tangible computer vision product or something by yourself. Please ask questions. I'm tired of talking. I'm gonna stop sharing. Yeah, ask. Go ahead, Timoto.
Good evening. Thanks for today's class. So my question is that is it okay to say that a neural network will behave like a linear model without activation function?
It behave like a yes, very correct. It behave like a linear model with activation function. Explain more. Okay, with
No,
activation function, it just gives you like whatever garbage.
exactly. Yeah, is it okay to say that statement? Is it okay to assume that?
Okay, yes, because in traditional let's say one layer neural networks, we call it linear regression. This same thing I told you, linear regression.
Mm,
I will explain it on Monday too. So you just do your thing and it give you result and you are gone. But it is activation function that helps us like make this thing to cut himself, and we can decipher things. We can call it binary classifier, whatever thing. But let me check. But the answer to that is yes.
all
So
right,
um no, let's check. Wait, let's check. Without activation, do we call? Yeah, the answer is yes, because
all
it
right.
is this activation function that helps us. It will just give you just result. It will just give you like this, just straight result, and it will just be good with your life. The mother will be singing song for you. Oh
Okay,
yeah, Motoro. I've been waiting. Moro, oh boy, yeah. Bello.
Okay, good evening. So,
Mm.
I just want to understand the difference between the computer vision and deep learning since we are connecting to end now. So, are we saying
Mm.
that before you can do like computer vision? Because I think I know people learn yeah, deep learning on its own, like in a broad sense. So I was saying that before you can go further in computer vision, you must know that deep learning too. Or I just want to understand what's the like difference between the two. Yeah.
Before you get into computer vision as an, before you be an, before you're an AI engineer, before you're a computer vision engineer, you must know deep learning, because it is after you build your computer vision pattern recognition, you do like your feature extraction, you need to pass it through a neural networks model. A neural network is deep learning. It is in neural network model, it is in that neural networks model that it actually learns. It learns if it is a human first, it learns if it is a cat or a dog, you see. So you must know deep learning, but I'm going to try to make sure I bring everything down. I teach the math, we build something simple, and then I assume like I didn't teach it. Then we now, because if you want to do it, we need to like we need a lot of heavy computer and the rest of the thing. But I need to make sure I teach you guys that deep learning, and I need to make sure I break it down so well. So on Tuesday, you guys should come prepared. We are going to do a lot, please. Yeah, but you need to know deep
Okay.
learning at least. You're not going to escape. I'm going to try my best, but you can't run away.
No, it's fine. Yeah.
All right. Are you guys okay? Do you have any question? Can we call it a day? I'm gonna give you guys an assignment right now. I'm gonna upload it in your. You should submit it on Tuesday. I need you guys to go and build a simple neural network model in Python and submit. So go and research how you should do it. A simple neural network model, a tool, just a simple anything you want to do. Build it and submit. It will give you more understanding, and do a video demo again, explaining why how you did it. Let me do that right now. I think we are done with the class. Thank you guys for joining. We'll continue on Monday.